Hello. Hello. Is anyone else on the line? Okay. Hello. Is this working? Hello. Hello. Carl. Hello.
Hello.
Hi, Carl. Can you hear
Hi.
me?
Yeah, it's very clear. How are you?
Is there any distortion?
It's okay. It's okay. I cannot see your video window, but I can hear you clearly. Yeah, I think it's okay.
Okay. So I'm trying to start an interview series with Kagglers, and I guess this would be a test run, and it should be posted on YouTube through Google Hangouts Live. I'm thinking I'll switch to something like Twitch, or depending on how it works.
Mm-hmm.
And I kind of want to interview Kagglers on their thoughts on Kaggle, but also machine learning in general. So yeah, that's kind of an overview.
Yeah.
So thank you for coming. It's,
Sure. Thank you for
I guess,
having me.
yeah, I mean, I guess it's like just the initial one will be an experiment. But hopefully we'll both get something out of it and it'll increase awareness in the Kaggle community as well.
Yeah. I really
So
like
I
the
guess,
idea. Yeah, I
oh yeah.
appreciated you could do it. Yeah, it's really great idea.
Yeah, and so I'm hoping the implementation will turn out okay. So kind of the agenda that I'm looking at is I do have some questions on kind of just Kaggle, and then the first part will be about Kaggle, and then the second part will be about machine learning.
Uh-huh.
And yeah, so just can you introduce yourself? And I know you're a top Kaggler. I believe you're a PhD student. So kind of give everyone else uh, just a short introduction.
Okay, sure. Hello, Mike. Hello, everyone. My name is Liu. I'm currently a third-year PhD student at University of Pittsburgh. So I major in computer architecture. So in my daily research, I also deal a lot with data, but usually the simulations and workloads analysis. So that kind of research. So it is about 2 years ago, or 1.5 years ago. So I have I studied this online course. It's very popular online course by Andrew from Stanford Machine Learning on Coursera, and that's the first online course that I finished. I mean, I watched every lecture and I did every homework. And after the course, I realized someone mentioned Kaggle, so I registered an account and I started to compete last April. So it's almost a year now. Yeah. And yeah, I think, yeah, that's it. Thank you.
So you've won 2 competitions on Kaggle,
Uh-huh.
and oh, sorry, you won 2 competitions on Kaggle. I believe they were TradeShift and the Microsoft. Can you tell us about your wins and just a
Oh,
brief overview?
oh, sure. So I have to say, so first of all, it's a teamwork. So in both competitions, I have a great team. And trade shift is a really special one because at that time, just I think 2 very great competitions just finished before trade shift. The first one is the Higgs boson particle contest, which is very popular, and the other is the click-through rate prediction. And in those two contests, I picked up 2 very powerful tools, the XGBoost and the Tingru's online FGD code. So I applied those 2 models in the trade shift, also plus a very strong benchmark from Dimitri. It's a very well designed 2-level models. So I combine all these 3 tools I picked up on Kaggle, and our team, so we put efforts in tuning the model. So we are really lucky in that case. The Microsoft malware contest this year is a completely different story. So it has a very large size raw data, so but not features, not no ready features for us. So we have to engineer or build every feature we use. So for this challenge, since everybody are using quite similar and quite simple models, so the major difference is feature engineering. And my background of computer architecture does help a little bit in the beginning of the contest. So we developed some very intuitive idea on how to engineer features. But as the time went by, It's more like a random experiment and the brainstorm with my teammates. So we discuss all kinds of different ideas uh, and we try all kinds of different ideas based on the papers and the other people's posts on the forum. So yeah, in the end, so we think we are really lucky that we stumble upon some very interesting and useful features. So yeah, that's my story. Thank you.
Yeah, congratulations. It's very difficult to win a Kaggle, and you won too. So, I mean, that's a great accomplishment. So, regarding the technical details, can you talk a little bit more on the intuition and ideas of two-level models and how you think that works and why it works well?
Okay, sure. So in the beginning, so it's we have access to this two-level model from Dimitri's benchmark. So after a while, so at that time we thought it works well because it captures the interactions of different classifiers. So in case of the trait shift classification challenge, and there are two kinds of features, so numerical features and categorical features. There is no single classifier that can both classify or both deal with numerical features and categorical features equally well, so or equally efficiently. So Dimitri's solution is to use simple linear model to train a hard-encoded categorical features and use a more complex nonlinear tree-based model to train the numerical models. So the predictions of these different kind of models can be a very good meta feature. So at that time, I think the reason is that they capture, they extract different information from this data set. So and also in case of trait shift, there's an opportunity that the training data is 2 times the size of the test data. So we can simply split the data into 2 parts for level 1 model and the level 2 model. So in that case, in level 2 model, we have the raw features and the meta features from the level 1 model. So after that, I read some blogs and listen to some talks of other data scientists. So it seems a very common practice. I mean, the 2-level model is a very useful practice for this kind of high-dimensional data problems. So it's especially when there are categorical features and with many levels. So and also in some cases in the natural language processing problems. So the 2-level model seems to have a very stable and consistent good performance. So it is confirmed. Yeah.
So Dimitri used, I believe, linear SVM in his original code. Did you use something else, or did you stick with SVM?
Oh, I tried something else. I started with linear models, so linear SVM and sklearn stochastic gradient descent (SGD) classifier. And in the very end of the contest, so I tried to use XGBoost to directly train one hard encoded categorical features. So that model is very slow, and because we have 33 labels in that case, so I have to train 33 models separately with XGBoost with one hard encoded features. It is very slow. So, however, in the end, it contributes a lot to the two-level features. So which is to my surprise. So it's yeah, the improvement is quite significant at that point. So I think, yeah, that's the trade-off. So the nonlinear model still can gain good performance, but the speed is very, very low compared to the linear models.
So was your final model, the first stage was XGBoost or was it random forest?
Okay, let me check that. So it's as far as I remember, so the first level models, we have several of them. So it's we have this online model, so which use the hashing trick to actually to treat every feature as a categorical feature. We have this online model, and we also have this random forest model, but only for numerical features. And we have this SGG classifier and linear SVM only for categorical features. And in the end, we add this XGBoost for one hot encoded categorical features. So I think
So
this is yeah.
You stacked 4 of them, all of them. You stacked all predictions.
Yes, all the predictions. So it's in that case, we have 33 labels to predict. So each model contributes 33 meta features.
Wow. So how is it possible that you didn't overfit in this case?
Yeah, I think. Yeah, so it's we tried 2 different data splits. So it's because in that case, as I said, the training data is 2 times bigger, 2 times the size as the test set. So it's we can try different splits of the training data for first level and the second level. So we tried random splits, and we tried the 50%. 50%, the first half of the training data as level 1, and the second half as level 2, and the opposite. So we find that in the cross-validation of the second level, the performance is slightly different with different splits. And moreover, the leaderboard score, the public leaderboard score, agrees with the improvement of the cross-validation. So at that time, we thought that since the level 2, the data for level 2 is completely isolated from the data for level 1. So we think we don't overfit data for level 2. And plus the fact that the leaderboard also reflects the improvement. So we think maybe we are not overfitting so much. Yeah, so that's just our thoughts.
Did you try 3-level models as well?
Yes, I tried. So it's we tried 3-level models. So it's the result is the performance, the improvement of local cross-validation no longer comes with improvements in the leaderboard. So in other words, the leaderboard performance is becomes worse. And so at that time we cannot stacking it furthermore. So the 2-level is the limit. Is the for 3-level we only have 1/2 data left for the 3rd level, and the performance is not good at all. So.
Do you think that 3-level models have potential if you use ideas from deep neural networks?
Yeah, I think so. So it's I think 3 model levels could actually work, but it just requires yes, as you said. So it's I think it requires multiple rounds of sampling or multiple rounds of different splits for the 3rd level data. So and plus, if neural network is applied in this case, I think if we bag a lot of networks. So we run it for a lot of times, and we run it for a lot of different splits for the third level data. So maybe it could gain a good performance. Yeah, but at that time we didn't try that.
So do you think that this type of multi-level model is, I guess, the future, given that it seems like people are already using three-level models? I mean, it's even possible that you are using three-level models if you consider the ensembling last step, right? You
Yeah,
got different
sure.
models. So, but more explicit three-level models, do you have any kind of, intuition regarding, do you think that last layer will always be like a linear regression? So in the case of auto, the winners used a three-level model where the last stage was weighted. So there were coefficients, multipliers, and then there was powers as well. So it was something like a times x raised to a power, something like that. The sum of. So that was pretty interesting. I mean, the power trick, I believe, is fairly common. There's more than a few Kagglers using that. And then there's the linear, the coefficients on each of the, I believe they use 3 different meta models, right? So, I mean, what are your thoughts on this type of, I mean, to me it seems like it looks like the architectures are similar to neural networks with these kind of feeding up, to a second layer and then to a third layer, and the final layer looks like a regression almost.
Yeah. Okay. I see your point now. So I just I didn't get your point for your last question. Yeah. Yes, architecture-wise, it does seem similar, and I think it's a great idea actually to build this kind of hybrid neural networks. In different layers, we use different classifiers and different, just as you said, so the last level is a simple linear regression, and the first 2 levels may be complex, and it has all kinds of different models. I don't actually have much insight for this architecture. So based on my practice, actually in level 3, we also tried very simple. So it's like weighted arithmetic mean or weighted geometric mean. So and that's it. So actually we don't consider it as a third level model because it's so much simpler than the first 2 levels. Yeah, I'll think more about your idea. So it does seem very similar to a neural network architecture, and it's this hybrid kind architecture is very interesting. Yeah.
So do you think that this approach will work for regression problems as well? I think one of the main advantages of multi-class, multi-label, it was, I'm getting my terms wrong, multi-labels, having multi-labels is that there's interaction between labels and so forth, and also in that case, you can find more information. So label 1 could be related to label 2, and your model, picks up on that when you use this meta approach. But if you're doing a regression problem, you don't get that benefit because it doesn't really exist. Yes. Have you tried this type of approach on regression problems?
Yeah, you have made a very good point. So it's the answer is no. So I didn't try this on regression problems, and I actually I think I didn't try it with single class or 2 class classification problems. Usually I try it with multi-class classification problem. So yeah, I agree with your point. It's this multi-level model, so it captures interactions with the multiple labels. So in my opinion, that regression is more easier to overfit. So it seems this stacking, this multi-level approach, I doubt it will get a good performance for regression.
But you haven't tried it yet.
Yeah, I haven't tried it. Yeah, I haven't tried it. Yes.
So I think that would be interesting to try.
Yeah, sure.
I'm interested in trying it also. So I did try using just the label. So feeding forward the label into a second, and it seemed like it was better than without it. So, but I don't know, and just the label as in the raw predicted class. That seemed to work, so I'm hoping that it will work for regression. But I also have not tried it in a Kaggle contest, so I'd like to see how that works. Okay, so yeah, that's great information. I kind of want to dig deeper into the tuning of these two-level models. I've noticed that these are unintuitive to tune. So a really good first-level model through cross-validation does not mean a really good meta version of the first-level model. So
yeah, exactly.
I don't understand exactly why this. So, for example, if I have 1,000 tree random forests, it usually does better than 100 trees. But I've noticed that 1,000 tree random forest in a two-level model, as the first level, is not very good. You want less trees, and it seemed like very strange and unintuitive to me why that would be the case, especially since in my cases, when I ensembled at the first level different models, it increased performance, so that seems like higher complexity. So I don't understand how to tune these models, but I also don't tune that much anyway, so I'm wondering what your thoughts are on what it means to tune a two-level model.
Yeah, so first, you made a very good observation that the good performance of level 1 model doesn't necessarily lead to improvement in level 2 model. So I don't actually have any evidence or but my experience. So in my experience, I adjust my thoughts. So I think the meta feature or the level 1 predictions, the most important thing for level 1 predictions is diversity. So it's you want these predictions to be different. You want them to capture different information, and sometimes when you improve the level 1 models of different classifiers, they actually become similar. So yeah, in terms of their performance, all of their performance becomes better, but they become similar. So when you ensemble them, I think the benefits may decrease. However, in practice, I cannot tell it. I cannot tell the difference when I have the level 1 model ready. So at that point, I have no idea. So if they can, if they are a good combination or they can contribute to level 2 or not, I have no idea. So I have to try to cross-validate the level 2, and by including and excluding different predictions from level 1. Only at that time, so I can tell, so it contributes or not. Yeah, but yeah, my general impression is that I will usually ignore the performance of level 1 models. So I just keep everything I thought that are different and put them to the level 2 and judged from the level 2 cross-validation score. Yeah.
So do you think that there's currently a lot of research in this area with understanding why? Because I think there's a lot of things that on Kaggle we see, but we don't know why. I mean,
Yes.
sometimes it works, sometimes it doesn't, but I can't tell you why it works. Do you know of the whys, or is this kind of still kind of dark for everyone?
Uh, yeah, I don't know why. So first, actually, so I don't read a lot of papers in the machine learning field. So it's but I guess yeah, I agree with your previous point. So it's this is this dark or black box of this multi-level model is very similar to the deep neural network, the thing we met in the deep neural network. So it's kind of a black art that the masters are really good at tuning this for each specific problem, but we don't get the reason. Um, yeah, that's my answer. So I don't know why either.
Do you have any intuition on whether you think weakening or noising data may help? So I had some thoughts on creating noise through artificially predicting features using out of bag. So I would, if I have feature 1 through 10, I would predict feature 1 based on 2 through 10, so the non-feature 1. And I don't know if this would work, actually. There's a lot of ideas I had for a variety of competitions, which I was never able to implement, but I noticed that having two is easy to overfit when you have many layers in neural nets and in different types of models. So have you investigated any ways of reducing overfitting besides, cross-validation? So like any tricks for reducing overfitting?
So I really like, so I tried one thing special in the malware challenge. So it's I borrowed the idea of data augmentation in the previous image classification challenge. So in the image case, so we produced some transformation of the original image, like shifting or rotating or something, to create more data and to overcome overfitting. So so at that time, I want to borrow this idea in our malware challenge. So the thing I did is that all the features we have are the so-called count features. So we count different events or different things. So I generate some random data for the. I think I generate 5% random data for the class that has the worst performance. So for example, based on our previous study, we find class 8 and class 9 has worst performance overall. So I generate 5% pseudo data, so whose features are randomly generated. So it's also a count feature, but randomly generated within 10%. So like 10% plus or 10% minus of the real samples. So we find that it actually improves probably leaderboard a little bit. So it's to our surprise because also our local cross validation. But in the end, so we don't trust this approach. So it's, we have no idea. So it can generalize well to the private leaderboard. So we don't select it in the end. But at that time, it's a very fun experiment to try.
Have you thought, I know you did some semi-supervised learning, have you considered an approach where you predict the class on the test with classifier A, use classifier B to predict the probability that the classifier is correct.
Yeah,
using correct out of bag, correct
yes.
CB, and then only take the test labels that have extremely high confidence that you're correct, and then augment it by using a different classifier than each of those on the larger augmented set. So basically, the intuition is, let me use more data, but let me be confident that I'm using more data using different classifiers, and then only on the confident augmented set, let me use a different classifier to try to get on some edge. I know you used some type of approach, some similar approach or some different approach, but used the semi-supervised approach. So what are your kind of thoughts on this data augmentation idea and using tests?
I actually we did try that. We did try one idea very similar to what you just said. So we try to predict. We try to predict if our predictions are right or wrong. So we try to predict which samples we have predicted wrong. So it's we try several different classifiers for doing this. We tried random forest and XGBoost to test to try to predict. So it's our previous predictions are right or wrong. So the approach is we first generate predictions for the training data set based on cross-validation. And we transform the label. So originally we have 9 labels for 9 classes. So we transform these 9 labels to one label, so 0 or 1, which stands for this prediction is correct or incorrect. So we have this data and we train XGBoost or random forest to see if we can predict which one is wrong. However, the result is we don't use the accuracy. The log loss of this prediction is about 1 order of magnitude larger than the previous prediction. So for example, the previous example we got this 0.007 log loss, and after transformed and we use this random forest, for example, to predict which prediction is wrong, our log loss is 0.07. So it's 10 times larger. So at that time we realized we cannot predict which classifier predict the confidence of each different classifier. So we find it's an even harder problem.
I see. So you did not go with that approach, though.
Yes. So we tried, but we didn't make it. Yeah.
But did you submit? So you did not submit to the leaderboard using that approach?
No, we didn't, because the CV result is quite. We don't have any confidence actually. So which classifier is trustworthy? So we don't submit it.
I see. That's interesting. So I guess what I'm wondering is your semi-supervised approach, was that dependent on the fact that the particular data set had extremely high overall accuracy? You could predict over 99 point something percent. You're very confident that you're right. Do you think this semi-supervised approaches would work in cases that are not like that?
Yeah, a very good question. So we tried it. So it does depend. It depends on the accuracy of the original classifier. So we tried a semi-supervised learning in the recent auto product contest. So the performance is very bad. So because in that case, the log loss is quite high actually. So 0.3, 0.4 at that level. So in that case, the accuracy of the classifier is quite low. So when we tried this semi-supervised learning again, so we found the performance is really, really bad. So it's worse than before. Yeah, so we guess this technique does depend on the accuracy.
So with your auto competition, what are the kind of insights that you gained out of auto that you did not know before auto? This is one of them you just explained,
Oh, yeah.
semi-supervised learning, but there must be many others.
Yeah. Yeah, for auto, the data sets. So we are only given, I guess, 90 features. So and all of them are count features. So it's we found that there's it is very, very hard to extract new information from this count features, from these features. So we are actually quite stuck. So we tried all the tricks we used in previous contests, malware contests and tree shift contests. So only two-level models seems to work in this case. So all the other tricks, so I mean the semi-supervised learning, the data augmentation doesn't work well here. So yeah, yeah, we didn't find anything new from this challenge. So until it ends, we read other people's approach. So thank you.
So do you think that the auto competition's data set was particularly difficult because, for example, or do you think the problem was ill posed? So what I'm asking is, do you think the features were not so good? Is that why it's a difficult? Or was it just some inability of the competitors, right? So the person who posed it was a top Kaggler himself, so I'm sure they had some internal models that did pretty well. What do you think about the particular problem?
Yeah, so I don't think the features are bad, or I think it is very real. So it seems a real data. So it's and for this particular problem, so we don't actually know what each product, what each class means. So they could have overlapped in nature. So we don't know that. I think just as the other Kagglers point out, so the feature seems there's no very strong or very bad feature. So every feature has some positive predicting power, but each one of them is very weak. So it depends on how you exploit all of the features together to squeeze some values out of it. So it seems the feature engineering is quite difficult. So, but yeah, the top one, the winners does try the very nice tricks to use the KNN to extract it. So it's other than that, I think it is very hard because this is a real world data set and a real world problem. So we cannot really achieve too high or too good performance.
Have you used KNN features before, or is this your first time seeing them?
I have seen them before. I think I may try them before, but it doesn't work well before, so we didn't try it this time.
I actually tried k-means and spectral k-means, different types of projected k-means, and they actually did not work so well on local cross-validation, so I did not try them personally. I'm not sure how they were able to make it work, but it was very different from how they did it, because I was using them as raw features to XGBoost. In the beginning of the competition, it's just really just kind of try to engineer stuff using XG. and I didn't see them working, whereas they used them as meta, and also they had many different models. So it's kind of difficult to judge. How do you judge features when it's possible that a feature in one model could be not so good, for example, linear model, or even a nonlinear model, and in another model it could be very good. So the obvious case is it's good in a nonlinear model and it's bad in a linear model, but it could be it's good in one nonlinear model and it's not so good in a different nonlinear model. And then there's also the case of the fact that you don't know if some subset of features combined in one model can ensemble well with another model with a different subset. So I mean, I guess the question is, how do you know which features to include and which features you don't, when the ensembling step makes it inherently a more difficult problem, which is already a very hard problem in the computer science sense, because it's a subset problem.
Yes. So usually I don't consider a single feature. So usually I consider a set of features. So to include or exclude a set of features for different model. So yes, one thing is intuition. So it's actually, I mean, the meaning or the deeper meaning of these features. So for example, in the tree-shaped classification, we have categorical features, but there are two kinds of categorical features. The first kind is the hashed features. So it's so as Triskelin points out, actually, so the hashed features are for the contents, I think, for the contents of the documents. And there are other categorical features which are simpler, which is not hashed. So sorry, I think there are yes or no features and other categorical features, but I didn't remember. So I remember that Trisklin's intuition is that the interactions of these hashed features may be useful, and he included this interaction of 10 hashed features in the online model, and it improves the performance a lot. So this is the kind of intuition I'm talking about. So if you know the deeper meaning of the features, and you may want to group those features together and exploit their interactions.
That's really interesting, because I remember in either the trade shift or maybe one of the online learning competitions after the ones with the big data sets and ad prediction kind of stuff, I noticed that having very strange interactions with no real meaning would actually produce public leaderboard increases, which in this case also are private because of the size of the data set. And they were basically really kind of stupid features, like max of 2 hashed indices, which doesn't really make any sense, or minimum, or like a mod or something, like doesn't even make any sense. It's like, why would you mod the sum of 2 hash indices, or why would you do a max when it doesn't? So I was wondering, like, why does this work? Is it because the regularization just takes out the ones that don't matter, and then you somehow get, I mean, it's not luck because it CVs both ways. So I've been wondering, how does this work? Because
yeah, so it's I don't really know, but my intuition is that, so if, as you said, this seems very dumb combinations of 2 hash with a slash in between. So it's I think it means it tries to capture if two events happen at the same time, or two hash appear at the same time in one instance.
Oh,
So,
no, no. I mean, I think the interaction is fine. I wasn't talking about the interaction. I was talking about, so the cat with, I understand how that works. You know, the co-location.
yeah,
Although I
sure.
did notice some weird behavior if you change the order. But I was talking about, I created my own features in those competitions that were like max of 2. So max of feature 1, comma feature 2.
Oh, I see.
So I created another one like minimum of feature 1, feature 2,
Oh, I see.
or I added them or multiplied them or modded them, and that doesn't make any sense because they're hashes. I mean, they're large integers, right? They have no real meaning numerically, yet somehow in some of those cases they improve the leaderboard. So I was using both the underscore interaction, but I was also using hash each and then take the max, or hash each and take the min, or take a mod, or take a, like, it's just weird stuff. Like it has no physical, like it should have no physical meaning, but does that mean the hash function is, does it have to do with the hash function? Does it have to do with, I don't know. I mean, I don't even understand why it worked, because some of it didn't work, but some did work. So
Yeah.
it's very strange.
Yes. Oh, yeah. Sorry. I see your point now. So it's that's kind of new to me. I didn't try to play with hash the results in that way. I think one reason maybe it somehow increases or decreases the hash conflicts. Maybe in some case increase conflicts is better, so you don't overfit, or in other cases you decrease conflicts. Maybe this new feature you created doesn't contribute, but it somehow, yeah, it affects the conflicts of the hashing. So I don't have much insight about the hash function. So, but I think it's a very cool idea to do to use this hashing trick, and yeah, it's also kind of black box to me. Thank you.
Do you think the hashing trick can be used in ways that are kind of beyond what you've seen it so far? I mean, so far it's usually for hashing to indices for the weights, correct?
Uh-huh.
I mean, that's the typical way that it's been applied. Do you have any insight on using like different types of hashing? Like, have you used locally sensitive hashing, or some special types of hash functions with different properties?
I didn't try different hashing. So I remember someone actually talked about it, about different hashing and the performance difference of the different hashing. But to me, I consider hashing as a very convenient type of mapping. So it's in any cases that I have no knowledge or I have no idea how to map these data, so I tried hashing. So it's a very blind experiment that I'm trying to do. So I'm just trying to see whether or not hashing can make a difference. So
do you
yeah,
use hashing, or do you use histogram? I mean, what's your first approach? Do you try the histogram features of counts, or do you go with the hashing?
It depends on the let me see. It depends on the type of features and depends on the data set. So Usually, so if the data set is quite large, so we have a lot of observations, I like to try the histogram count. So, but if the data size is quite small and or we have very few positive instances, I try to avoid histone count and try to use this hashing trick. Yeah.
Wow, okay, that's interesting. So I think, at least for the first session, we'll be targeting ending it within the hour. So I'd like to kind of wrap it up here and just, well, first, thank you for being the guinea pig for the first run. I have no idea how this will turn out, but hopefully it'll turn out well. And I guess the closing question is, do you have any questions for me regarding Kaggle or data science?
Yeah, sure. So first, thank you, Mike. Thank you very much for doing this. And my question is that what is the most important difference or the biggest difference you find between the Kaggle computations and your daily data science research?
So I think there's a big difference in applied data science in terms of what clients want and the kind of things that you would see in Kaggle. And I think the biggest difference is that visualization is a lot more important in, I think, a lot of people who have jobs in industry. And I don't think it's as important in Kaggle. I don't think there's any emphasis on understanding the data at a visual or intuitive level.
Yeah, sure.
And I think I actually like Kaggle, but I did notice that the TSNE features were particularly good, and I wonder if there's something more to understanding the kind of the bigger picture or the projections. And it makes me wonder if things like k-mean features or nearest neighbor features that have geometric or visual appeal can also be used in Kaggle. So having both help other people understand, like management or people in industry or clients, through visualization, but also having it be extremely useful in terms of machine learning. So I think that's a big difference, and I think the crossover is using visual intuition for both telling the story behind it, but also for engineering the features, either algorithmically or not. So because I don't see Kaggle as parameter tuning contests. I know some people see it as like it's just a parameter tuning, and I don't spend a lot of time doing parameter tuning unless it's algorithmic. And I think that's a big kind of difference, is that I don't know. So for auto, I have no idea if I could have done better if I tuned the models I used. Because I did tune, I mean, it would be a total lie to just say, oh yeah, I didn't tune them at all. But definitely if you look at the models I posted, they were not, I don't think they were heavily tuned.
Yeah, I see.
It was, for example, if you look at the number of rounds for in the bag, it was like 60. So people were using like 1,000 XGBoost iterations, right? So I mean, I clearly didn't see it as, I don't know if it would have helped. Maybe it would have hurt. I don't know. See, the thing is, I don't know. I just know I have some intuition, but I have very little. I do hand tune and learn, and I know the intuition that for some reason in these meta bag models, it's counterintuitive, but yeah, I mean, I think I'm talking too much about that stuff. So yeah, I mean, there's a very close tie between how you visualize data, how you graph data, how you tell the story behind the data, and the features you can see in a contest, which can help performance. But I don't think most people care about the performance.
Oh, okay, that's good to know. Thank you.
Thank you very much. Hopefully we'll get this posted. And it was great talking to you, Carl.
Yeah, me too. Me too. Nice talking to you.
Okay, I'll see you next time. Bye.
See you. Bye bye.
Oh, did this work? This is the first time it worked.
Oh, hi.
Oh, I guess, does it end here then? Wait, did that? Okay, well, I guess it ends here, unless it didn't work. Okay, bye.
Bye bye.
How do I? Bye.